is that we're going to have a listing. What we have is what's called a discrete random variable. A discrete random variable is discrete in the fact that it has to be single units. It can't be part of a unit. Can't have 1.5, 1.3, whatever. And they only can take certain values. And typically we refer to this as by a capital letter. Now, this notation in here, this is a probability distribution table. And basically what they're saying is the only values that this discrete random variable x can take is 1, 2, 3, 4, and 5. And then each probability is associated with those values happening. Now, since every one of these, all these probabilities line up with the only possibilities that are, available, these probabilities are always going to add up to 1 on a probability distribution table. So, in a situation like this where they've got some variables, all we do is make an equation out of it and then make it equal to 1 and then get the A by itself. Did you do that?
Yeah, I got that part.
What'd you get for A?
I don't have it with me right now. Give me
Oh, all
one
right.
second.
Well, let's think about it. What's point 0.2, point 0.1? That's point 0.3. Point 0.3 is point 0.6, point 0.7. So basically what we're going to end up with is point 0.7 plus A equals 1. A's got to be point 0.3, right?
Right.
So if I make it point 0.3, now the other possible thing, and then this is a very common thing to do, is give you a variable and then have you figure out what that variable is. And all they want you to do is make it equal to 1. And this, if I ask you for the probability of x being greater than or equal to 2, well, that means all I do is add up these probabilities and get a total probability. This is a probability of getting a 2. This is a probability of getting a 3, a 4, and a 5. But if I want to know the probability of getting anything bigger than a 2, including 2, I add those all up.
Yeah, I think I got 1 and 2. What about like 3 and 4 and like the ones after that?
So in 3 and 4, we have to actually build the probability distribution table. So here we've got a spinner and it's got 4 parts, numbers 1, 2, 3, and 4, and a blue spinner, 3 parts, 1, 2, and 3. And the sum of the numbers are going to be my random variable. So the first thing I'm going to do is figure out what those are. How would I figure that out?
So you'd have to like make a good chart and see what the sums are.
Yeah, exactly. So we've got 1, 2, 3, and 4. And then we've got 1, 2, and 3. So 1 plus 1 is 2, 3, 4, and 5. 3, 4, 5, and 6. 3, nope. Try that again. 4, 5, 6, and 7. Now, by conducting this experiment of what they said, we've spun, we got these spinners and we've come up with all the possible outcomes. What are the values that x could possibly be?
2, 3, 4, 5, 6, and 7.
So what happens is that we're going to make a probability distribution table. The top row are what the things they could be, and again, it's a small x, so it's possible to have a 2, a 3, a 4, a 5, a 6, and a 7. And then down here, I'm writing the probability that my random variable, which is a capital, is equal to this little number. What's the probability of it being a 2?
1 out of 15.
1 out of 12,
I meant yeah, 12.
right? What's the probability of being a 3?
2 out of 12.
Exactly. Now, the thing is, with probability distribution tables, I know that a lot of times we're hung up with fractions that it's wrong if we don't simplify it, and it's perfectly okay to leave these not simplified. What's the probability of getting a 4?
3 out of 12.
And then 5?
Also 3 out of 12.
And then 6?
2 out of 12, and then 1 out of 12.
And see, the reason that it's okay not to simplify it is because it's very easy for me to go and add these up and make sure I end up with 12 out of 12 and get a probability of 1 when they're all added up. Okay, so do you remember that problem today we did on a quiz? It was a similar thing, only they were dealing with marbles. What's going to happen is that, because we're filling with probabilities, building a probability distribution table, you may have to find the probabilities of all the different probabilities of something happened. Does that make sense?
Yeah.
And so that's all that's happened here. We've taken this situation, we've found out every possible thing that could possibly happen, and we've also figured out the probability of each one happening. Now, generally, it won't be super difficult to do. Like you can say, once we've built this chart, it's pretty easy to come up with the numbers and their probabilities. But that's all we're asking. And see here, we've got 8 letters in the mailbox. 5 of them are addressed to Christian. So Christian removes 4 letters from the mailbox at random. Create a probability distribution table N for the number of selected letters that are addressed to Kristen. All right, so there are 8 letters altogether. 5 of them are addressed to him. What are the possibilities? If N is the number of letters addressed to Kristen, if I'm pulling out 4.
0, 1, 2, 3, and 4.
Is it possible that there's 0?
No, because it's half. It's more than half.
Yeah, you get me? So if you think about this, there are 5 for him and 3 not for him. So the reality is if I'm pulling out 4, 0 isn't an option. But what is the lowest option?
1.
It is possible there's only 1. It is possible there's only 2. It is possible there's only 3. And how many did I say we're pulling out?
4.
4. So it is possible that there are 4. Right?
Right.
Now, what's the probability? So we would say these are my little x's. Then the probability that my discrete random variable takes those individual values. What's the probability of only having 1?
Oh, is this the one where you have to choose?
Well, we could. So let's think about this. If we're choosing for him, how many are for him? 5.
Yeah.
And here we're going to choose 1, right? In this situation, we're only choosing 1. That means what do we have to choose for the other ones?
3.
3, choose 3. Now, what are we dividing by?
Is it 8, choose 4?
Because I have 8 things and I'm choosing 4. So now, this is going to give me the probability of only getting 1 of them. Do that for me. Tell me what it is.
And we're multiplying 5, choose 1, and 3, choose 3, right?
Yeah, and then dividing by this. Just set the whole thing up on your calculator exactly like that. Use that fraction button. You know what I'm talking about?
Yeah, it's equal to 1. Wait, I think I might have done something wrong then. It's 1 over 14.
1 over what?
14.
All right, so we'll put that here. Now, in your calculator, if I go to the next one, if I'm going to pick 2 letters for him, this is going to become a 2, and this is going to become a 1. So just go to your calculator and make those 2 changes and tell me what that probability is going to be.
Three over 7.
And so now if I have 3 over 7, and see now I'm going to have 3 of them for him, so this is going to become a 3, and this is going to become a 1.
Also 3 over 7.
And then the last one is that I have 4, so this can be 5 choose 4 over 8 choose 4. This last one is going to become a 0.
1 over 14.
So we have 1 over 14. And see, you can see if I double this, this becomes 6, this becomes 6, and so then it's 6 and 6, and that's 12. 12 plus 2 is going to be 14. When I add these all up, I will get a probability of 1. And again, so the purpose, the idea, though you may have to build a probability table, is it shouldn't be super long and drawn out. It shouldn't take a whole long time. So either it's going to be relatively straightforward like this, where you build a possibility chart, but I see this happen a lot where there's choosing going on. Because again, once you set it up, you can crank out several probabilities pretty quickly. Any idea? So when you're building a probability distribution, they're going to give you some kind of scenario. You've got to find that every possible thing that could happen, and then the probability of those things happening.
Yeah, I got it.
All right. So what about 5?
Is the 8, 9, and 10 like the possibilities of it?
That's what they're telling you. Notice how they use capital Y? In this case, they're telling you the random variable Y, and they're telling you that the only possible things that can happen are 8, 9, and 10. Now, what happens sometimes is they give you a formula for figuring out the probabilities. The probability that capital Y equals little y, and remember, these are little y's, is equal to k times y. All right? Now, that's a little y. So what's the probability of getting an 8?
8k.
And what's the probability of getting a 9?
9k.
And what's the probability? Yeah. Okay. So what happens is, by giving you this formula, it's just turning it into the problem like number 1 or number 2, where you've got to find out what k is, and then consequently what the probabilities are. In this case, 8 plus 9 plus 10, that's 27. K is equal to 1. What's k got to be?
1 over 27.
And see, keep in mind, that's what k is. So what's our probability going to be?
The probability of y less than, that's 8k plus 9k.
Well, in this case, what's 8? What's the problem? This is supposed to
8
say,
over 27.
Yeah, because all I'm doing is multiplying what my k is, right? So this becomes 8 over 27. This becomes 9 over 27. This becomes 10 over 27. And now I have all my probabilities. Now, what if I ask you what the probability of y being less than 10?
That's 8 over 27 plus 9 over 27.
Yeah, we just add them together.
I got it.
All right? And see, it's going to be the same kind of thing with this one, only it'll be squared. It'll be some number squared, but it works pretty much the same way. And see, then we're finding the expected value. And again, we talked about this today in class. When we had a frequency table, to find the expected value, we multiplied each number times its frequency, and we added them up in a probability, and then we divided by the number of numbers. Do you remember?
Yeah.
Okay. Well, with a probability distribution table, it's pretty similar, only what we're going to do is just multiply the numbers times their probabilities. So this is going to be 0.2 plus 0.2 plus 0.6 plus 1.2 plus 1.0. All I'm doing is multiplying 1 times 2, adding this up, and that's going to be the expected value.
Yeah, I got it.
All right. Now, variance what we do is take each number and square it times its probability and add them up, but then we subtract the expected value squared. So like when we had the frequency tables, very often they have you find the mean first or the expected value first because you're going to need to use that.
What is the variable? Can we do one of the examples for variable?
Yeah, for variance you mean?
Variant, yeah, variant.
All right, so, well, first, here, let's do this. Help me find A. Oh, here, we'll do this one. All right, so do me a favor, because I don't have it in front of me. What's the answer to this? What's the expected value?
$3.2.
All right, so 3.2. All right, and again, if you take a look at it and think about it, take a look at these probabilities. They're pretty even, except for you'll notice how it's a little bit heavier towards here with the 0.3. And so I would expect that it's probably going to be a little bit more than 3. But you can see how this is half, and these two are half. So you can see how that the mean is probably going to be somewhere a little bit above 3. Anyway, if I'm going to find the variance now, the variance of x is going to be 1 squared times 0.2 plus 2 squared times 0.1 plus 3 squared times 0.2 plus 4 squared times 0.3 plus 5 squared times 0.2, and then I'm going to subtract the expected value, the expected value squared. And again, that's the variance. If the question were to ask for the standard deviation, then I would take that value and I would find the square root of it.
Okay, I got it. Are all of the rest of the questions like that?
Yeah, so you'll notice here, it just kind of mixes some things together. You have to find the A. Once you find the A, then you find the expected value and the variance. Here you'll notice there's, what's different about 5? You notice how there's 2 different variables?
Mm-hmm.
So what happens is we have to build 2 separate equations. One of the equations, 0.1 plus 0.2 plus 0.1 is 0.4. So that's going to be 0.4 plus A plus B is equal to 1, right?
Right.
All right. Now, what equation could I build if I knew the expected value was equal to 3.4?
That's the, so you can like, is it?
How do I find the expected value of a table?
Is it like with A divided by 4 and
How
B divided by?
did I find the expected value? What did I do?
You multiply and add them together.
And see, the difference is, in this case, when I do that, I'm going to have these variables, but this is still going to be 0.1 plus 0.4 plus 0.3, but then it's going to be plus 4A plus 5B, and what's that got to equal?
3.4.
And see, then what I can do is get one of these variables by itself and then just solve it like a system of equations. I know if I can figure out what A is equal to, A is going to equal to 1 minus 0.6. And once I know what A is equal to, I can take this, simplify all these numbers here, and replace that A with what it's equal to, which is 1 minus 0.6. And then I have an equation that only has B's in it, and then I can solve it. Oops, not 0.6, B. Duh. 1 minus B. B, duh. 1 minus 0.6 is 0.4. Let's try that again. 1 minus 0.4 is 0.6, and so it's going to be 0.6 minus b. That's what a is equal to, yeah?
I think so, yes.
Okay, but these two are just a system of equations. You make one equation out of this whole row equaling 1, and then you make another equation by taking this times this and adding this times this and adding this times this and adding this times this and this times this, and then making it equal to 7.4. Once you have two equations, you take the simplest one and get one of the variables by itself, and then substitute back into the other one.
Okay. Yeah, I got it. Are these going to be the only possible questions on the test, or
Yeah,
are there
pretty
gonna
much this is pretty much what you got to worry about.
Okay, thank you.
In a probability distribution, it's about building a table, finding the expected value, dealing with these variables if they have them in there, and find expected value and variance. This is, essentially the extent of what you have to be able to do.
Okay. I think I'm good for 6.1.
All right.
For 6.2, I have part A, but I haven't done anything for the expectation and variance part. So can we do a few of those?
6.2.
Yes.
6.2. Whoop, wrong one. Where did my 6.2 go? All right, where are we at?
The expectations, number 7.
All right, so in a binomial distribution, all you got to do is multiply the number of trials times the probability of success to get the expected value. So for this case, for number 7, what's the number of trials?
20.
And what's the probability of success?
1/4 to 0.25.
All right. Now, all I got to do to find the expected value is multiply those together. What's 20 times 0.25, or divided by 4?
5.
Okay? Now, if I want to find the variance, all I do, that was n times p, right? All I'm going to do for the variance is n times p, which is the number of trials times the probability of success, but then take that and multiply it by the probability of failure. So if you will, if this is n times p, I can use that for this part of the formula, because that is equal to n times p, but then all I got to do is multiply it times the probability of failure. What's the probability of failure?
0.75.
Exactly. Now sometimes what will happen is they'll say that the variance is equal to n times p times q. It's really common. Well, first, the probability of success being p, very, very common, okay? The probability of failure being q is also very, very common. I prefer to refer to it as 1 minus p, because sometimes what happens is there are situations where if we have to build an equation and we only have one variable, it makes it a lot easier. But that's essentially it. Anytime you have a probability distribution and it's a binomial, you have to have a fixed number of trials and you have to have a probability of success. And so if you do, all you do is multiply them together to get the expected value. So take a look at number 8. Oh, we do need to talk about this. So take a look at number 8. Number 8 says that extensive research has shown that one person out of every 4 is allergic to the grass seed. So you'll notice this is the same situation. The probability of success is still 1/4 or 0.25. Okay? How large of a sample? So in this case, we don't know what n is. Would be needed for a probability to be containing at least one allergic person to be greater than 0.99. All right. Now, did you do problems of this stuff here, like 1, 2, 3, 4, 5, and 6?
I did. I did all of them.
And you feel good about them?
Yeah, I didn't write it like all the answers out, but like I like looked at it and like
All right.
yeah.
Because what happens is this problem is based on this premise. All right. So now here's the thing. I know that it's a binomial distribution. I know that the number of trials is n, and I know that the probability of success is 0.25. Now, if I write the probability statement is going to be that I want to know the probability that x is at least 1. What do I write when I want at least 1?
Greater than or equal to 1.
Okay? Now, here's the situation. If I was doing this, and say, for example, there were 3 trials, what would I do? If I knew, forget this problem. If I knew the number of trials was 3, and I knew the probability of success was 0.25, and I wanted to find this probability of, what would I do?
You use the formula and find the probability of getting 1, 2, and 3.
Exactly. Okay? Now, the problem in this case is I don't know how many trials there are. So I can't go up and build all those. Now, the other thing is that what if it was what if the n was 10? Well, now they want you to do the probability of 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. What would be a lot easier to do?
The probability of 0 and then 1 minus that.
So if I do 1 minus the probability of 0, that's the same thing as the probability of x is greater than or equal to 1. Does that make sense?
Yeah.
Now, this is kind of a contrived question, though I've seen it more than once. And what happens is that it's based on, they make it look like this, all right? But what you're going to have to do then is rewrite it as 1 minus the probability of x equaling 0. This thing where they're trying to find n, it only really works, and I'll show you one exception to this, when I'm finding the probability of x equaling 0. So let's go ahead and do this. What would the combination be? Even though I don't know what n is, what would go on top?
And choose 0.
And then the probability of success, which is 0.25, would be to what power?
0.
And then the probability of failure would be 0.75, and it would be n minus 0, or n. Yes?
Yeah.
All right, now, they want this probability to be greater than 0.999. So do you see how I'm just changing these words into this statement here? Right?
Yeah.
All right. So basically, at the end of the day, one minus this, because this is the probability of 0. So if I do 1 minus that, I want it to be greater than 0.99. Okay? Now what's any number choose 0?
Is it 1?
And it's all, 5 choose 0, 10 choose 0 is always going to be 1. Any number choose 0 is going to be 1. What's any number to the 0 power?
Also 1?
Also 1. And see, that's why this problem really relies on the fact that we're finding the probability of 0, because then both of these will end up being 1s, leaving me with 1 minus 0.75 to the nth power is greater than 0.99. So how can I get this 0.75 to the n by itself?
Is it like to the nth root?
Well, but again, if it was an equation and I was trying to get this 0.75 to the n, how would I get rid of the 1?
Oh, the 1, you would subtract it.
Yeah, what's 0.99 minus 1?
Negative, um, 001.
Okay, you with me on this? Now it's negative, right? Now what's over here? You see how this is a negative over here?
Mm-hmm.
So what if I divide both sides by -1?
Positive 001.
Okay, but what is also going to happen to my inequality sign?
It's gonna have to flip.
So now it's going to be less than. You with me? And now it's this. All right. Now, do you remember in Math 3 when we were trying to find something in an exponent? If I'm trying to find something in an exponent, do you remember using logarithms?
Yeah, I was gonna ask his logarithms.
All right. Logarithms have bases. What's this base?
Is it 0.75?
Exactly, because it's a thing we're raising to the power. Now, what do we end up with?
0.001.
That's also my logarithm, because logarithms are going to equal exponents. So now in this case, I'm not going to put equal, I'm going to put less than n. Now, you got a calculator? Do you see on your calculator like 2 buttons below the menu button?
Yeah, the log button.
Use that and tell me what log base 0.75.001 is equal to.
24.011.
So
24.012.
24.0 what?
012. Can I round?
Yeah, because I really don't care. Because keep in mind, this is a number of trials, right?
Yep.
Then we're finding a number of trials. It has to be a discrete number. Now, you'll notice how if I rewrote this so n was first, it would say n is greater than 24.01, right? So what's n got to be?
25.
25.
Okay, yeah.
Okay? Now, this is... take a look at number 11. It's the same kind of thing. What's our probability of success?
27.27.
And then you'll notice that they want to know how many races. Now, each race is a trial. He either wins or he loses. So I don't know n again. Now, I'm not sure this is worded the best, but again, you'll notice how, again, it's probability of at least 1. The probability of at least 1 is equal to 1 minus the probability of x equaling 0. And then the probability of x equaling 0 is going to be 1 minus n choose 0, 0.27 to the 0. And in this case, what's it going to be? What? 73?
Yeah.
And again, that's going to be the n. Now again, greater than 0.95. Now do you see how it's pretty much the same thing? N choose 0 is going to be in 1. 0.27 to the 0 is going to be a 1. I have to get this 0.73 to the nth power by itself, so then I can use a logarithm to find out what n is. And all I'm going to do is treat it like an equation. I'm going to subtract it. I'm going to divide by -1, which will flip this sign. I plug in that logarithm, and then I get a number. What happens is, The only time I've ever, well, there's another situation, but this is not very hard. You can take a look at number 10 in a minute. But here they're asking you to find the value of n. But most of the cases, if they try to find the value of n, it always looks exactly like this.
Okay, yeah. So it's not gonna ask you for like if it's at least 2, you just do
Well, like I said,
probability
even
one.
if it yeah, but the problem is, and see, that's the thing. Say if it was at least 2, well, then it's going to be the probability of 0 and 1. That's not going to work because then one of these numbers aren't going to be zeros. Does that make sense? It only works if these end up canceling out and becoming nothing. So it almost
Right.
always ends up being the probability of 0, not even anything else.
So it's always gonna be just asking for at least one.
Yeah.
At least in this
Okay.
particular.
Now, go down here and take a look at number 17. Well, look at number 16. What are they talking about in this case?
The probability of it being 0 is greater than 0.1.
But in this case, this is the probability of x equaling 0. So I don't need to do 1 minus anything. I'm just going to do this straight across. Does that make sense?
Yes.
Because up here, I couldn't do it the way they wanted me to do it, and I ended up changing it so it was the probability of 0, right? In this question, it starts off with it being the probability of 0, being greater than something. So I'm going to do 1 minus. Now this one is a little bit different. Look at number 17. How would I do this one? So again, they're telling me what they want. The probability that Q is equal to N. So how would I do that? What would the first thing, what would the combination be?
And choose. Is it N?
Because remember, like that combination is going to be N choose 0 for this one. Up here it was N choose 0 because it's always going to be wherever that number is. In this case, we made it a 0, right? So yeah, it's going to be N choose N. And then what's my probability for the 0.96, right? What's that going to be? To what power?
To the N
And then the
power?
next one's going to be 0.04, but what power is it going to be?
0.
All right. Now, again, greater than 0.5. But once again, what's 5 choose 5? What's 10 choose 10?
1.
Once again, these two cancel out. And I'm
Yeah.
still left with 0.96. Now to the nth is greater than 0.5. I make a logarithm out of this and then find out what my answer is. So here's an exception of where it won't be greater than or equal to 1, and then you have to change it. Here, they just start off making it equal to 0. You don't have to do anything. And here's where they make it equal to n. But in both these cases, two of the things in my formula are going to cancel out.
Okay. Can you go back so I can take a picture of 8 and 11?
Yeah.
I got it. Thank you.
Now take a look at number 10.
So is it just 5 divided by 0.04?
We know that P is equal to 0.04, and we don't know N, right? But we do know the expected value is 5, right? So since the expected value is equal to N times P, all I got to do is take 5 equals N times 0.4, and then divide it.
Right.
Okay? So that one's just taking the expected value formula and kind of working it backwards. Anytime like, yeah, I've seen questions about n this way, and I've seen questions about n this way. But what happens is, no matter how you slice it, they're all pretty much like these 1, 2, like number 8, number 11, number 16, and number 17. They once you get them set up, they're pretty much the same exact question. They don't happen like on every test, but when they happen, they usually look like this.
What about 12 and 13?
So here we've got the Binomial Distribution. They give us the expected value and they give us the variance. So think about this. How do I find expected value?
N times P.
And we know that that's going to be 2.7 is equal to n times p, right?
Mm-hmm.
Now, tell me about the variance. How do I find the variance?
It's 2.7 times 1 minus P.
Well, let me just give me the formula. It's going to be, yeah, exactly, right? Because n times p is that. So if I do 2.7 times 1 minus p, and what's the variance?
2.214. So it's just a system of equations.
Well, yes, essentially yes. Once I figure out this, I just substitute into this, and see, I got one variable, and so all I got to do is get it by itself. And see, here's an example. If you remember the formula was being for variance was equal to n times p times q, well, then what would happen is that you wouldn't realize that these are the same things, and it makes it harder to do.
Right. And for 13, is that like the same thing?
So, no, in 13, what are they telling you? What does this mean?
Oh, it's just the
What's the first number?
N is 8 and P is 2/7.
All right. So what happens is sometimes they'll give you a word problem and they'll ask you for the parameters. And when they ask you for the parameters, they're asking for this. And it's also possible that they would just give you a problem that says this. And basically they're trying to figure out, do you know what this means? Because if you don't know that this is n and this is 2, that this is probably a success, well, then the whole problem stops for you, right? But that's really
Right.
all this is. So 8 choose 4 times 2/7 to the 4th times 4/7, no, 5/7 to the 4th.
Oh, so this is just what's in the front. The front.
Exactly. Do you see what I'm
Okay.
talking about? It's the same thing, only it's not a word problem. If you think about it, what happens is you take a word problem and then you change it into this, and then you do this. Well, here, they're giving you those two things to make sure that you actually know what those mean.
Right. The other ones were so complicated. I thought this was more
Yeah,
complicated.
no, it's actually easier. As long as you know what the notation means, it's actually easier.
Okay, I got this one.
So keep in mind, when a binomial distribution, it has to have a fixed number of trials. There has to be only two possibilities, success or failure. The probability of success has to be constant, and the trials need to be independent. They can't be, one thing happening can't affect another. And you'll notice, and like I said, these problems, there's some assumptions we kind of have to make, but that all that kind of stuff is going on. But there's nothing to lead us to believe that they don't. In a geometric distribution, there will never be a fixed number of trials. There will be only a reference to a first success. That's all I care about, is when do I get the first success? Are you good on this one?
Yes. You said you're gonna post the answers to all these.
Yeah. As a matter of fact, I was going to, and I was looking for it, and I think I left them on my desk. So tomorrow, because I notice I've got the answers to one of them, but I don't have the answers. I've got them written, but I don't have a digital copy. and I'll make sure and post it tomorrow.
Okay, thank you. For geometric distribution, I'm looking at number 12. Um, what is the probability? Yeah, it's like number 12 on 6.3.
Okay, let it open up here. Okay, so what are we looking at?
Number 12. No, like on the first page.
Oh,
It's the
sorry.
last question. You're fine.
All right, so how do you find the expected value?
It's just 1 over probability.
So what's 1 over 0.2?
Just 5.
Okay, now basically what they're saying is find the probability that x is less than 5. Now keep in mind, in a geometric
Oh.
distribution, what does that mean?
That you can find whatever you need to find within 4
But what am I
tries.
looking for?
The first success.
So what they're saying here is, what's the probability that the first success happens on either the first, second, third, or fourth trial? Does that make sense? It's not
Yeah.
saying that I want 4 successes. I just want to know the probability that the first success is either on the first, second, third, or fourth trial, right?
Mm-hmm.
And again, they talked about this today. There are 3 formulas. When it's equal, which I reverse it, I actually kind of think of it like this. I think of failures, so if I'm looking for the probability of x equaling some number, say 7, then there have to be 6 failures first. So whatever the probability of failure is, I put that to that power. Then there's going to be 1 success. And so then I put the 1 probability of success, okay? That's the formula that's on your sheet, but it's written this way.
Mm-hmm.
The 2 formulas that are not written on there are these 2. And they are just as important. Like, it's incredibly likely that you're going to be asked questions greater than or less than.
Yeah, those 2 I got.
All right. So, in this case, which formula are we going to use?
This one is less than, so technically the third one, but we have to subtract 1 because it's not
So
or
we're going
equal
to actually find the probability that x is what? Less than or equal to
4.
4. And see, then all we got to do then is 1 minus the probability of failure, which is what?
0.8.
To this power.
Right.
And see, from mistakes people have made in the past, it's always a great idea to rewrite it in the way that you want. Because the one nice thing about the probability distribution or the geometric distribution, this number is always going to be the power when we're doing less than or greater than.
Mm-hmm.
So then all you do is, multiply it or raise to the power and subtract it from 1.
Okay. Yeah, that one makes sense. Are all these questions in the back, like questions that we've gone over?
But see, the trick is that they're mixed, and you have to identify which one. For example, in the first one, number 1, Logan's lighting a fire. Each attempt has a 1/3 probability, independent of each other, of lighting. Find the probabilities of getting it to light. So the question is this a geometric distribution or a binomial distribution?
Binomial.
Why?
I'm sorry. Geometric.
Why?
Because he tries infinite times until the fire gets lit.
Exactly. Now, if you want to think of it this way, You notice there's no specific number of trials. That's a
Mhm.
requirement for a binomial distribution. And also, if you think about the process of lighting a fire, do you keep trying to light the fire after you've lit it? No. Okay? So that's why we're only looking for one success. I light it and then I stop. So this is a geometric distribution. Now take a look at number 2. Logan's got to light a fire. Each attempt has a 1/3 probability. It starts off looking exactly the same. The difference is it says Logan attempts to light it 6 times. Find the probabilities. Now here, this is a binomial distribution. This question says every time I light it, what's the probability of it lighting twice out of the 6 times? In the 6 times.
That's the 6 choose 2 and then
Yeah,
the
see,
whole.
this is a binomial. Do you see what I'm talking about?
Mm-hmm.
You have to also be careful because sometimes, weird, look at number 4. In a game of Monopoly, the player has to stay in jail until they roll doubles. What's the probability of being in jail more than 3 turns? What is that? A distribution.
That's geometric.
Because once I roll doubles, it stops. I'm out of jail, right?
Mm-hmm.
All right, so then take a look at number 9. 8% of the males are colorblind. What's the probability that the first 5 men checked, none of them are colorblind?
That's binomial.
Right. Because you know, the number in this case, the key here is that we're trying to find the probability that x equals 0, that there is no success. And see, in a geometric distribution, there has to be a success. Just one, but there has to be a success. Now, take a look at B. What's the probability that the first colorblind man is found? Is the 6th one checked? This is clearly a geometric because that's all I care about is the fact that he's the first.
Mm-hmm.
All right, now take a look at 7. 2% are 2% are rejects. What's the probability that the first defective chip you find is one of the first 5?
That's geometric.
And then B, what's the probability that 3 of the 20 chips are defective?
Binomial.
Okay? The idea is, what happens is because they both have 2 possibilities, they both have a probability of success, sometimes people have difficulty distinguishing between which one's binomial, which one's geometric.
Mm-hmm. Can you go back to 12 and 13 on 6.2? Sorry, I forgot to take a picture of that one.
Sure. Oh, you know what? I think I got rid of it.
Oh, okay, that's fine then.
I think I just... Let me see if I can save it. No, I think I just X'd it out. Let me make sure it's not here. No, I just X'd it out. Sorry.
I think I remember it. I just wanted to make sure I had something to look back to, but I should be okay.
So just keep in mind, as far as a binomial distribution, it's a number of successes in a number of trials. We don't care when, we just care about the number. And that number could be as low as 0. In a geometric distribution, there's only one thing we care about, and that's when the first success is. And like I said, sometimes it'll be just as plain as that. They'll say the probability of the first success happening, but other times you have to kind of think about whether there are more successes than just the one. Well, like for example here, he shoots foul shots. And see, here, they tell him to shoot until he misses one. So again, in this case, what am I focused on?
The missing, so it's the
So
20%.
yeah, exactly. What you also have to be careful with is that sometimes they give you a probability, and again, the probability of success doesn't always have to be good. In this case, because I'm interested in what he's missing one, the probability of success is actually zero point 0.2 when he misses it. And see, that only happens once. Because once he misses, we stops. So sometimes what will happen is they'll give you a probability, but it won't be the one you're interested in. It won't be P.
What is the what must we assume part?
So in this case, he's shooting foul shots. We have to assume, because this thing, each shot is an independent trial. We have to assume that each shot is independent. He doesn't get fatigued. He doesn't get tired. The fact that he's made 3 in a row doesn't make him less or more likely to make the next one. Does that make sense?
Yeah.
And since he's human, I mean, it's possible he could get fatigued. It's possible that he makes 5 in a row and he starts to lose his concentration. I mean, there are different factors. We're assuming that the trials are independent.
Okay, yeah, that makes sense.
Giovanni, you got any questions?
Can we go over permutations?
Yeah, what do you want to know?
I was wondering if we could review some of the questions from the previous test.
From the test? Hang on, let me see.
I think I'm good on permutation, and my laptop's dying, so I'm gonna go now. But
All right.
thank you.
Have a good one.
You too, thank you.
Permutations. What'd you say? The test, right?
Yeah,
Let me
I
find
took the pictures of each question, so I saw like the work I did, and I just want to ask some questions.
Okay, cool. Oops, that's not the right one. This is the right test?
Let me check. Yeah, that's the right one.
What question do you want to look at?
I was wondering if we could go over question 2.
All right. So,
Well, I have multiple questions, but I want to focus on like what's gonna be on the test. All right.
right.
So
we can talk about whatever you want, man.
all right, bet. So question 2, right? So for the first part, I got 2 points. So I did it right, but I was wondering if you could like go over like when would we use like bars and stars, and when would like multiply by place? Cause like I feel like I get it, but like I really don't. You know what I mean?
Okay. So, in this case, it says find the number of ways in which 10 letters in the shopkeeper can be arranged. We're doing the right one, number 2, right?
Mm-hmm.
No, it says arranged so all the vowels are together. So that means it's going to be like this. And then what are my non-letters? S, H, P. How many P's are there?
There are 2, I believe.
2 P's. And E's we already know about. And so then R.
There's only one R. Yeah.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Whoops, I'm missing something. What am I missing? K. Right?
Mm-hmm.
All right. So number one, whenever I do a problem like this, I pull them apart so I can visually see it. But then I make sure I count to make sure I have the same number of letters that I haven't screwed up in my rewriting, right?
Right.
Okay. So in this case, they have to be together. Now, how many things do I have if they're together?
We have 4.
No. How many things do I have?
Oh, just one.
That's just one. How many things do I have altogether, though?
You have 1, 2, 3, 4, 5, 6, 7.
Okay. Those are the things I'm rearranging because these guys all stay together, right?
Right.
So how would I figure that out?
You'll do 4 choose, well, not 4 choose, 4 vectorial divided by.
Let's start with this. How do I arrange these 7 things?
That'll be 7 vectorial over 2 vectorial.
Because there are 2 duplicates, right?
Mm-hmm.
Now, in every one of these arrangements, the letters are, my together guys are in the order of E, 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 O. Now, they're allowed to move around, aren't they?
Mm-hmm.
So I have to multiply, for each one of these arrangements, I have to multiply by the number of ways this could be arranged, which was what you started to do. How can I arrange these?
You'll do 4 vectorial over 3 vectorial.
Does that make sense?
Yeah, that makes sense.
Whenever you're keeping a group together, count the group as one thing, then do it just like you would arranging, but then you've got to multiply by the number of ways your group things can be together. Now, if it had just been 3 E's, well then it would be 3 factorial divided by 3 factorial, and that would be 1. Does that make sense? Because 3 E's can be arranged only in one way. E, E, E.
Yeah.
But the fact that there was an O, we had to take that into consideration. Okay, you good?
Yeah, I feel good about that.
All right, so now in B, what's it say?
It wants to find the number of different ways in which the 10 letters of the word shopkeeper can be arranged so that the P's are not next to each other.
All right, so once again, now the P's are not next to each other. So what are the non-P letters?
S, H, O, K, and the 3 E's, and then R.
And then I've got PP, right?
Mm-hmm.
Now, whenever they say, now, in this case, it's only 2 things, okay? If it's only 2 things and they say they're not together, then you're still going to do stars and bars. If it's more than 2 things, so say for example, say there were the E's, and we said the E's couldn't be next to each other, then you have to be really careful with the wording. If it says all of these are all, are not next to each other, well, what that implies is that the 3 E's are not together, but the 2 E's would be okay. Does that make sense?
Mm-hmm.
But when there's only 2, there's only one way. If they're not together, that means they're separated. If I have 3 E's and they're not together, well, that could mean there's 2 E's. Does that make sense?
Yeah.
If there was 3 E's and I didn't want them together, then I would probably use the words that I didn't want any E next to each other, or that the E's had to be separated. Anyway, whenever the 2 letters cannot be next to each other, is when I do stars and bars. And like I said, these are the guys that are separating my p's. And then my p's can go in these places. So how many ways could my non-p's be arranged?
8 different ways.
8 factorial? 1, 2, 3, 4, 5, 6, 7, 8. But how many more duplicates?
3 of them, so we got to divide by 3
Because keep in
factorial.
mind, I'm still arranging these non-p's, right? Whenever you're arranging something and they're duplicates, you've got to divide by the number of duplicates. Now, I'm going to multiply times the number of places I can put these p's. Well, where can I put the p's? How many places do I have?
9.
9p2, right?
Yeah.
But once again, I'm arranging these, but you'll notice my p's are identical. So what do I have to divide by?
2 factorial. Yeah. Right.
Okay?
Yeah. All right, and then so like once like we got to like C, that's like when.
When we get to what?
That's when, like once after that that's like when things just went downhill. Like I got some points, but
All right,
yeah.
so look at C. Here, what are they telling you?
It says that they want you to find the probability when E is at the beginning and E is at the end. Or in E, yeah.
So that means there's going to be 8 things in the middle,
Mm-hmm.
and the E's are on the ends, right? Now keep in mind, whenever they give you some kind of specific thing like this, where the E's are on the end, well, in every arrangement, where are the E's going to be?
They're gonna be one's gonna be
They're on the ends, right?
yeah.
So as far as my arrangements, they're all going to have an E at the beginning and an E at the end. So that is never going to change. So it's not part of what I'm figuring out. What I've got to figure out is how to arrange these guys in the middle.
Right.
Right?
Mm-hmm.
So what's left for the middle?
8 factorial.
Well, but let's think about the letters. What are they? P, P, S, H, O, K, E, R. 1, 2, 3, 4, 5, 6, 7, 8. Right?
Right.
Now again, I'm arranging these things in this middle space. How many are there? How many ways can it be arranged?
The spaces like it's
Yeah.
the letter.
Well, these letters in these spaces.
Would it be 9
Well,
or
how many things am I arranging?
8?
And how many are duplicates?
2.
See, at the end of the day, I'm arranging these letters in these spots, right?
Right.
It's still arranging that number factorial, and I'm still dividing by the number of things, right?
Mm-hmm.
All right. Now, find the probability that a randomly chosen arrangement of 10 letters of the word shopkeeper has an E at the beginning and an E at the end. All right. So that means we got to consider all the possible ways to arrange the letters in the word shopkeeper. Right?
Mm-hmm.
Did we have to figure that out already? Nope, we didn't, have we? Okay. So I was going to say, I don't know if that was in the part or not. So how many different ways can these be arranged with no restrictions at all?
25,200.
Because how many letters are there?
8. Oh no, not 8. 10.
10 letters. Because find the probability that a random choosing arrangement has got an E at the beginning and an E at the end. But keep in mind, I'm taking it out of all the possible words that can be made out of this word, right?
Mm-hmm.
So that includes ones that don't have E's on the ends. So there are 10 letters I'm arranging. How many are duplicates?
two of them, so it'll be 3 choose times 2 choose.
Yeah, exactly.
I'm not choose, but Victoria. My
Yeah,
bad.
exactly. Okay? Now, this is the total number of ways those letters can be arranged. This is the total number of ways they can be arranged if they've got 2 E's on the ends and these guys are in the middle. So you take this number and you put it over this number. This is the number of ways I'm interested in. This is the number of ways that word could be arranged without any restrictions at all.
Yeah. That's where I messed up on.
Okay, but does that make sense?
Yeah, that makes sense.
When you're finding a probability, I need the probability is the list of number of things that I'm interested in divided by the total number of things.
Right.
And then here we're talking about selecting. And see, are you okay with this or no?
No, I did.
All right,
yeah.
so again, we're taking 4 letters and we're selecting. And see, now I know we're switching to combinations. Okay?
Mm-hmm.
Now, again, notice how they're telling you that I'm taking 4 letters, but there is exactly 1 P in it. Now, this is what I talked about. When I have permutations, when there's a duplicate letter, there's a way that we deal with it. We divide by that number of letters or whatever they are, factorial. Okay? The problem with combinations, there's no part of the formula that we do that with. So what we've got to do then is kind of look at the different scenarios. In this case, my first scenario, clearly has a P, right?
Right.
So now how many other letters are there? 3, right?
Yeah.
Now what's the duplicate letter?
E.
And see, this is the thing I have to take care of. So let's do this. I've got E's, right?
Mm-hmm.
The P I'm not worried about at all because the P, there's only going to be 1 P and there's never going to be more than 1 P, right?
Right.
Okay? So what are the letters that are not E and are not P?
S, H, yeah. R.
And R, right?
Yeah.
Okay? Now you get what I'm going on here?
Yeah, I see where you're from.
And if I add them up, 1, 2, 3, 4, 5, 6, 7, 8, but that's because I'm not talking about the 2 P's, right?
Right.
All right, now, what I've got to do is try all the scenarios that are possible with my E's. What's one scenario with my E's?
You can have all 3 of them.
All right, so if I do that, this is going to be one way, okay?
Okay.
If I choose 3 E's out of 3 E's, there's only one way to do that. Does that make sense?
Yeah.
All right, so now again, what's another scenario?
You can get 1 S, 1 H, and
No. Focus on the E's.
Okay. You can get 2 E's and a different letter.
So this is 3 E's because this is the part I have to take into consideration. The E's. So the first scenario is there's 3 of them. Now what if there were just 2 of them? Now there's still a 4th letter, and what am I choosing from?
Those 4 letters.
So that's going to be 5,
Right.
choose 1.
Oh, okay.
Okay? Because really, these have to be set. What I'm saying, because in this arrangement, there is a P and 3 E's. There's only one way for that to happen, and so I've written it down. Here, this scenario, there are 1 P and 2 E's. So this part has to be, there's only one way for that. The only thing that can change is this last digit. And there's 5 ways for that to happen. Now, what other choice do I have for my E's?
You could only get 1 E
I
and
can
then
only get 1 E. Now, if I only get 1 E, now there's 2 places for letters. How many am I choosing from?
you do 5 choose 2.
Right?
Yeah.
All right, so now what's 5 choose 2?
That is 10.
That's going to be 10. Now, what's the other possibility?
You can do P without any E's.
Exactly, because you'll notice the only requirement is that it has a P. There's no requirement that it has an E. We're just exploring we're just looking at all the different ways, but it's also possible that there is no E at all. So then this would be 5, choose 3. And that's going to give you that number.
And then so after that, you just add up all the different ways and you get your answer.
Yes.
Oh, so like what I did, I disregarded the 3. So like what I did, I had no idea what to do. I'm not gonna lie, but I had to like write down the letter P. But instead of like doing all of that, I just wrote the 3 other lines and did A choose 3.
Right. Okay.
So like that wouldn't.
And see, there's the thing. But out of those 8, 3 of them are identical.
Oh, okay. So that's what I can't. Well,
see,
let's say that.
What happens is when I'm choosing identical things, it's like the arrangements, they offset each other. But the problem is there's no way for me to take that into account, so I've got to break it apart. So just think about it. Like I said, when you're arranging something and they're identical things, you're going to have to divide by it. When you're selecting or choosing something and there's an identical thing, then you've got to spell out every different scenario. Now notice that they have made it so there's exactly one P. What would happen if they didn't do that?
You could have another P, or you could have duplicates. Yeah, you can have duplicates, right?
Exactly. And see, the reason they've done this is to make the problem easier. Because if I would have also had P's that repeat, well then it's possible there's one P. Then it's possible so these would still all exist. That's with one P. But there's also the same number of them with 2 P's.
Yeah.
And then I would have to play out the E's then, and then the non-E's. Does that make sense? So the reason they've made it so it has to have a P is so you didn't have to worry about the fact that there was 2 duplicate letters, that all you have to worry about is the one.
Yeah.
But whenever you have a combination and there's a duplicate, just get ready to play out the different scenarios of having a duplicate. And it's possible that, like, if we're not choosing everything, then it's possible that there's none of your duplicates. We could have no E's, 1 E, 2 E's, or 3 E's. And see, if you think about it, that covers all the possibilities.
Yeah. All right. So round question. So if like there were any duplicates, would that work? Like what I did? Like so, like let's say that I like the same situation, but like all like there's you know what I mean? Like each letter was different. Would that work out or no?
Yes.
So that would work out?
If there was no duplicates, then that would be the right thing to do.
Oh, okay, yeah, okay, that makes sense.
The only reason it was the wrong thing to do was because there were duplicates.
Right, okay, yeah, that makes sense.
When I'm choosing out of this group, the fact that there's duplicate things, it affects the number of choices.
Yeah, that makes sense. All right,
by the way, what number did you get when you did 8 choose? What did we say?
I got. Oh, my phone.
You got a much bigger number, right?
Yeah, I got 56.
Right, and the reason it's so much bigger is because you counted each one of these E's as separate things. But the reality is, selecting these E's are interchangeable. It doesn't really change anything. And so there's going to be a lot less possibilities.
Yeah, that makes sense.
All right. What else you got?
Oh, so I have a question on number 3.
What's that say?
It says find the number of ways a committee of 6 people can be chosen from 8 men and 4 women if there must be at least twice as many men as there are women on the committee.
All right. So again, here's another situation where we have scenarios. So let's do men and women, right?
Right.
Now, I'm picking how many people?
You are
Like, well, how many are in my committee?
6 people.
All right. Now, let's just think about this. What's the least possible number of men there could be if there has to be twice as many? At least twice as many.
1, right? Or no?
If there's one man, are there twice as many men?
Oh no! It would 8. So like no wait no. No, I messed up here.
Because remember, these two numbers have to add up to 6.
Yeah. So you could have 4 men and 2 women.
All right. So
Okay.
if there are 4 men and 2 women, that's twice as many men, right?
Right.
Go backwards. What if there was 3 men and 3 women? Does that meet the criteria?
3 men. 3 men and 3 women.
Yeah. Does that meet the criteria?
No, right? Because it
No.
has to be at least twice as many.
Exactly. So that means it has to be bigger, right?
Yeah.
Now, if I had 5 and 1, is that at least twice as many men as women?
Yeah.
And what if I had 6 as 0?
Yeah, that's at least twice.
That's
Yeah.
right? Okay? Now,
Yeah.
how many men did I have to choose from?
8.
So this is going to be 8, choose 4, 8, choose 5, 8, choose 6. How many women did I have to choose from?
4.
So that's going to be 4, choose 2, 4, choose 1, 4, choose 0. Now keep in mind, this is one committee that I'd be happy with. It's got 6 people, 4 men and 2 women. This is one way that I'd be okay with. This is another committee that I'd be happy with. It has 6 people, 5 of them are men and 1 of them is a woman. I'm happy with this. This has got 6 people and more men than women, twice as many. I'm also happy with this. The reason I multiply these together is because in order to get a committee that I'm happy with, I need both of these things. I need my 4 men and my 2 women, so I've got to multiply them together. I add these up because I'm happy with these, and I could take this or this or this. They all are fine, and I add them up and I get the total number of ways that would make me happy.
Yeah. Wait, so you would multiply because like that's a possibility that can occur, right?
I'm multiplying it because in order to get a committee, I need both of these things to be true. I need
Oh,
4 men and 2 women.
okay.
Both of these make one committee, so I've got to multiply them together to get the total number of ways.
Okay. Yeah. Well, I only did 4 choose 2 and 8 choose 4 and multiplied that.
What'd you do? 4 choose 2? Oh, right. Now, that's the key here. That's twice as many, but it says at least twice as many.
Yeah.
Okay? So that means that there still could be more than just that one way. Now, if we take out the words at least, then when your thing says, if it says there must be twice as many men, well, see, then there is only one way to make me happy. There has to be 4 men and 2 women. Only one way to make me happy. But because it says at least, these are also ways that could make me happy.
Yeah, that sounds good.
Does that make sense?
Yeah, that makes perfect sense. That clears up. And so for part B, how would we go about that?
In a situation like this, where we're picking a committee and we want to know about the number of committees where 2 people are not ever going to be on the same committee, it's much easier to figure out the total number of committees and then subtract the number of committees where the 2 people are actually on it. So let's try this. How many people are on my committee?
6.
Now, there's two people, two men. Okay, so two men that refuse to be on the committee together, right?
Right.
All right, let's make sure. Find the number of ways the committee of 6 people can be chosen from 8 men and 4 women. Now, do you notice how this problem doesn't have any criteria about number of men or number of women? Okay?
Mm-hmm.
All right, so here I've got my committee. The two people that hate each other are on it. Okay?
Mm-hmm.
1, 2. They're on it. Now, how many other places do I need to fill?
4 more places.
Okay, now, again, in this case, remember, I don't have men and women. What do I have?
You have people, yeah.
Because you notice there's no requirements for men and women. Okay? So really, how many people do I have left if 2 men are already on the committee?
4 people left.
Well, no, how many men are left?
Oh, 4, right? No, 6, yeah.
And then 4 women, right?
Yeah.
How many people do I have left?
You had some people, okay.
Okay, now remember, in that previous problem, the requirement was something about men and women. There is no requirement here. So all I gotta do is figure out how many ways to choose 4 out of 10. Does that make sense?
I think, yeah.
That's
I think
gonna
so.
give me the number of committees that have men and women, or whatever, because it's also possible that it could be all men. Okay?
Yeah.
But the 2 people that hate each other are on the committee. Now, how many ways can I find a number of ways what's the total number of ways I can do it?
10 different,
How many people do I have altogether to start with?
8. Well, no, 12.
I have 12 people, right?
Mm-hmm.
So if I do 12, choose 6. That's the number of ways to choose 6 people out of 12. Right?
Right.
What's that equal?
That gives you 924.
Now, what does 10 choose 4 equal? Because this is the total number of committees I could make out of 12 people and then making committees of 6.
10 choose 4 gives you 210.
210 is the number of committees that have the 2 men on them that hate each other.
Okay, so
if I take away 210, what's left over?
714.
That's the number of committees where the people that hate each other are not on it.
I did something I don't know what I did. So like what I did, I took away the 2 men, right?
Yeah.
And I did similar. It was similar to like the previous question. I did like
So you just
W
took them
and
away?
N.
So you considered 6 men and 4 women?
Yeah, I was like gonna choose like every single one, and I was gonna equal it to like 6 committee members.
Well, yeah, but there's all kinds of iterations of that,
Yeah.
right?
Yeah.
And that's why I'm saying when they have a small number of people that can't be together and they're choosing, it's easier to figure out them being there and then taking them away from the total number of ways to do it.
All right. So 12 choose 6. Okay, the 12 represents like the total people, and then the 6 represents like how many people can be in the committee, right?
Yeah.
And then the 200, we get 210 from, you take away the
You
2 people.
You said this is equal to 210, right?
Yeah, 10 choose
And
4.
that's the number of committees that have these 2 guys on them that hate each other.
And so, I'm trying to so wait. Okay, so we Oh, okay, okay. I think I got it. I think I got it. Yeah. Yeah. I think I understand it.
So this is me taking 12 people and choosing
Mhm.
6 of them with no restrictions at all.
Mhm.
That's how many ways I can make 6 committees, or committees of 6. This is the number of ways that I can make the committee with the requirement that these 2 men that hate each other are definitely on the committee. Now, if I take that away, that means that I never have a committee where these 2 men are on it. One of them could be on it, because there's no requirement that this man by himself can't be on the committee, and no requirement that this man can't be on the committee, just that the 2 of them both can't be on the same committee.
Yeah. Yeah. That makes a lot more sense. That makes a lot more sense.
All right, cool.
And so,
We're
all right.
good.
This is
Any other ones on here? I think isn't that all the permutation ones for this one?
well. This is kind of embarrassing. But I have a question on the 5. Like I thought I was gonna get easy points on that, but I
Oh,
don't know what had happened.
what number? Which one?
All I don't know what happened to my brain.
All right. So find the probability the random chosen student is at Canton College and prefers hockey. Where's Canton College?
With the numbers 22 and 56.
And which one of these? So all of these students are from that college, yes?
Uh-huh.
How many of them prefer hockey?
56.
Now keep in mind, these are all college students, right?
Mm-hmm.
So how many college students do I have altogether?
500.
So the probability is the number of things I'm interested in. I'm interested in these 56 divided by all the possibilities. This is all the possibilities.
Uh,
And I think you divided by either 78 or
yeah, I
240.
divide by 78. So like it wouldn't be 78 because that. So
That's
what?
that's the probability that someone likes hockey is from Canton College.
Okay, that's yeah. Because I originally had 56 over 500, but I was
Yeah,
overthinking and yeah.
you're overthinking it, okay?
Yeah. And so for B, I did 180 over 280, but
So
that's
what
wrong.
probability that the random choice student at the VAR college prefers soccer? So again, did you do 120 divided by 500?
Oh, I think no, I did 120 over 280.
Oh, hang on, let me see here.
Oh no,
Oh
I did
wait, this
100.
is given. All right, notice how it says given. I didn't catch the word here.
Uh-huh.
All right, so what's the probability that the chosen student is at the VAR college given they prefer soccer? So if it's given they prefer soccer, we can look at it two different ways. The probability that they are from the VAR, given they prefer soccer, could be the probability of them being both. What's the probability of being from the VAR and preferring soccer?
120 over 180.
Well, I don't know, 500.
Oh yeah.
Okay? What's the probability of preferring soccer?
Um,
How many people like soccer
280.
out of 500?
Mm-hmm.
But when I divide these, it really becomes 120 over 280. Okay? Now,
Uh-huh.
again, you don't have to do what we just did here because
Mm-hmm.
it says find the probability that random choosing is from the VAR given they prefer soccer. That means that it has to be out of this number of people.
Yeah.
Do you see what I'm talking about? Here I take 120 and divide by 280 because it's given that they are like soccer. That's why I'm not going to divide by 220 or the total because it's given to me that they have to like soccer. That means that I'm only going to divide it by this group.
Uh,
So you can do the probability of both, divide by the probability of the given, or you can use the table that way.
Alright, yeah. Yeah, that makes a lot
And
of
then
sense.
see, one of the students chose at random. The event is they prefer hockey and they're at Amos College. Wait a minute. Or, let's see, what's it say? One of the students who chose a random determine whether the events a student prefers hockey and the student is at Amos College or Ben College. All right, so let's say this is A. What's the probability that a student prefers hockey?
Um,
How many people like hockey?
220.
Yeah, how many?
In total,
220?
yeah.
All right. One of the students is chosen to determine whether the events a student prefers hockey. Okay? So there's 220 of them. The probability of that happening is 220 out of 500. Right?
Mm-hmm.
All right. Now, the other event is that they're at Amos or Ben. So that's those two numbers, right?
Right.
What are those two numbers added together?
242.
So that's going to be 242 over 500. That's the probability of B. Okay?
Mm-hmm.
Now, what's the probability that a student prefers hockey and is... Now here I'm... Because we said this is B, right?
Mm-hmm.
Okay? Now, remember, if I want to prove they're independent, I have to show the probability of A times the probability of B is equal to the probability of A and B. But like we talked about, you don't find the probability of A and B by multiplying these two. How do I find the probability of A and B? I'm looking for people that prefer hockey and are from those two colleges. So, which ones? These two prefer hockey and they're from those two colleges. Isn't that true?
Mm-hmm.
How many is it going to be?
That's 104 people in total.
So that probability is going to be 104 over 500. You with me on that?
Mm-hmm.
Now the question is, if I multiply this times this, does it equal this? If it does, then they're independent. If it doesn't, then they're not.
Okay. Yeah.
Okay?
Mm-hmm.
This is like we talked about that other problem. If defined independence, I mean, in this case, they literally think of this as meaning and. They have to want the probability of them being from those colleges and liking hockey. These are the people that are from those colleges and they like hockey. Does that make sense?
Yeah.
So then, this is the number of people that are from those that like hockey. These are the people that are from those colleges. If I multiply these together and they equal this, then it's independent. If they don't, then it's not.
Yeah. Yeah, that clears up a lot of things.
All right, good. All right, I gotta run. You got anything else?
No, I think that's all. But wasn't actually so like I should. So you know the permutation problems. You know how like they follow a pattern, but each one's unique, right? You like should I just like keep on practicing the problems and like review the permutation videos to like get it, or
Try practicing them. Now you know I can't remember if you were there, but I made another video on permutations and combinations.
Mm-hmm.
Were you there for that one?
No, I missed that one.
You might want to watch that video and just try to like pause it and try to work the problems and then watch to see if it, what they say.
Alright, yeah,
And that might help you too.
yeah. But I
And
really
then
do
try
appreciate.
redoing problems that we already did.
Uh-huh.
See if you can do them without looking.
Alright. Yeah, but thank you, Mr. Cross. I really do appreciate this. Really,
All
really
right.
help.
Have a good one now.
Yeah, have a good day, Mr.
All
Cross.
right, you too.